just start with that. I get my understanding of it. So firstly, you show that isomorphism is somehow truly reducible to the minimal size circuits, minimal circuit size. That shows really hardness, so minimal circuit size.
That's a pretty weak hardness because graph isomorphism isn't so hard.
Value at least that shows it's probably, if there's a P, then graph isomorphism has an easy hardness. So now the next result is that based on this, we try to show that two different reductions. That gives some kind of surprising results for P-space computers. Let's work on it.
Thanks. So thanks for coming back to the exciting finale. Last time I had put these two statements on the board and promised a proof, and I still want to give the proof. We're looking at a particular problem. It's minimum oracle circuit size problem where the circuits have an oracle for the standard P-space complete problem. This gives rise to something that's complete for P-space under probabilistic reductions, but it's not complete under log space reductions. And rather than jump right into the proof, I'm going to continue to tell the story about how all this fits together, and then I'm going to go back and fill in with details about some of the proofs. So what is another fact about this problem? MCSP QBF is not hard for P under log space, actually Turing reductions, unless P space equals X. So this statement says if you look at what's log space reducible to this problem, you don't get all of P space. Well, what do you get? Probably you don't get very much at all. In particular, you don't even get P unless something very strange happens. Why am I mentioning this now? QBF, or MCSP to the QBF, is P-space hard. So in particular, it's a lot harder than, and so MCSP is easier than MCSP QBF. This should be obvious, right? This is in NP. This is P-space complete. This thing, the harder thing, almost certainly is not hard for P. So surely this can't be hard for P under log space reductions either, right? Well, we don't know that. We don't have any theorem that says that. So we do know MCSP hard for NP under even much more restrictive reductions. AC0 many one reductions implies what? NP not NP poly. And we can say much more, but let's say exponential time is not in size 2 to the epsilon n. Both of these are due to Ryan Williams and his student Cody Murray. But this is the same type of result that we had back in lecture 1 that we credited from Tsai and Cabinets. If MCSP is hard for NP, which we don't think is true, then a bunch of stuff that we think is true anyway is true. You know, we don't have really strong evidence for MCSP not being NP complete. It's just, if it were NP complete, then we would know stuff that we would dearly love to know, but we don't know. So why does this result here not tell us that MCSP shouldn't be hard for NP? It's because we have currently no efficient deterministic reduction from this easier problem to this harder problem. Sure, there's a probabilistic reduction, a ZPP reduction, but that's all we know. In particular, we don't know anything like a log space Turing reduction. So when we proved this result, we thought this is actually the sort of evidence that we want to say MCSP is not hard for NP. Because it would just be really strange if a very unlikely consequence were to follow from this hard problem being hard for P, and then this easier problem somehow actually being harder. But as we've proved more, my thinking has evolved so that yeah. Good.
Why can't you just forget the oracle and just MCSP going to MCSP?
Why can't we just forget the oracle and
get a reduction from MCSP to MCSP to relativize the PBF? I mean, just forget the oracle and just say, I'm happy, I'm in here if I'm in here.
Okay.
Well, because we don't know how to do that.
Well, Rob, I actually have a question even before yours. So how do you define as an oracle, based on MCSP?
So what is MC?
What is a host of machine?
That's right, because it's
MCSP QBF
Yeah, what is that?
is the set of, your input is a bit string of length 2 to the k, so it's a Boolean function, and a number I, and you want to know if f has QBF circuits of size less than or equal to I. So what's a QBF circuit? It's a piece of hardware. It's got AND gates and OR gates, and it's got QBF oracle gates. And what's the size of this? Well, pick a size that you like.
why couldn't you just leave it out?
Well, if you leave it out, that's a different problem. For instance, QBF, we don't think has small circuits, right? So if you have the truth table for QBF here, it's probably going to require really big circuits. But it's got really small QBF circuits, right? One oracle gate. So it's a different problem.
Your intuition misleads you. It's not like recursion theory when you apply an oracle. It's just a different problem.
So there's no host machine for any of this.
Just a parameterization of the problem. It's a different problem.
So QBF is P-space complete.
QBF itself is p-space complete under really restrictive reductions. This problem is also p-space complete if you allow much more generous reductions, but not if you use even reasonably generous reductions like log space Turing. So now that I've got you maybe to appreciate why this is so messed up, maybe I'll launch into the proof of that to see, so you can maybe appreciate what's going on. But is there, yeah, question?
Why couldn't you just identify circuits which lack those gates and say, I want to know if this thing's valid, I just
You're not asking about circuits, you're asking about the existence of circuits of small size.
You're given, the main thing here, so it's really a question about Kolmogorov complexity, something you know something about. Yeah. So if you want to know if a function is random with one notion of randomness, it doesn't mean you can answer is it random with another notion of randomness. That's what's going on here. These are two different this is basically space-bounded Kolmogorov complexity. And MCSP here is wherever I wrote this problem, this is time-bounded Kolmogorov complexity. These are different notions. Okay? So, actually, I'm happy to take questions here before I launch into this proof.
Let me ask another question. In your second line there, okay, so isn't that just implied that you start that
So this
zero is really including L, right?
AC0
Many one.
is, so this is a much more restrictive notion of reducibility.
General, right? So that really means that your second line here implies that.
This is MCSP with no oracle.
Well, but if with the oracle it's not even piece space complete, can that still be without oracle? Can that still be hard? In that case,
That's the question. Almost certainly this is not even hard for P under a pretty powerful notion of reducibility.
right.
But this problem could still be NP complete. We do not know how to disprove this.
Yeah, but it's something like this, with those facts, that assumption seems very unlikely.
This assumption seems very unlikely.
But then in that case, what is the meaning of, assume a very unlikely factor and then proving something? Since if it's unlikely, if it's not true, then it's always true, right? This is whatever you can get.
So the reason that this is an interesting result is because we actually care about whether this problem is NP complete under some reasonable notion of reducibility. And this is the strong, we would like to, in fact, get a stronger conclusion here. The conclusion, false. But we don't know how to do that. In fact, all we get is a conclusion that is probably true.
Right.
But, true, but we don't know how to prove it is still a strong conclusion. The question is, yes, I agree with you. This result, even though I think it's a nice piece of work, it sucks because it's not where we want to be. We really want to be able to say this conclusion implies false. Ryan Williams certainly is on record as saying that's where we want to go. But this is the best that we have yet. Yes?
You say then that this is a result not about truth, but about what's provable in current technology.
Yes, but every result that we can prove is...
No, but this kind of says, well, if you're hoping to prove that the top is false, then you have to know how to do something else that we also don't know how to do right now.
Question?
Could it be possible that NC is harder than with the oracle? Because you're basically saying, are there small circuits? And
In fact,
yes, if I'm allowed to use those gates,
Actually, I'm going to hold off on the proof of this because I'm going to present some theorems that will kind of answer your question. So I'm going to jump ahead just a little bit. All of these results, if you replace MCSP with MKTP, this theorem still holds. Thus far, I haven't presented anything where that's really different. That's going to change. So I'm going to leave that up there because I still really do want to prove that. But I'm going to have things we can prove for MKTP and not yet for MCSP. Okay. Recall from last time, graph isomorphism is in RP to the I'll say MCSP because that's what we proved. It also holds for MKTP. Here's a theorem. Graph automorphism is in ZPP to the MKTP. Graph automorphism, does anybody need me to define that? Okay. Exactly. And in fact, graph automorphism is polynomial time Turing equivalent to rigid graph isomorphism. So for rigid graph isomorphism, your input is a pair of graphs, each of which has no non-trivial automorphism, and you want to ask, are they isomorphic?
Is that a promise problem?
It's a promise problem. And, if you think about it, in some sense, this ought to be the hardest instances of graph isomorphism, because either there's no isomorphism in general, or possibly there are a bunch. But in the rigid case, either there's none or there's exactly one. So if you're just searching through a big space, just the case where there's only one needle in the haystack is intuitively, maybe the intuition's bad, but intuitively that's the hard case.
But count graph isomorphism is reducible to graph isomorphism.
Say that again?
Isn't the counting problem the same as
The counting problems are the same for everybody who understood that question. Yes, if you want to count how many isomorphisms there are, if you want to count how many automorphisms there are, those problems have the same complexity.
Doesn't that suggest then that intuition is not necessarily correct?
Well, in fact, our intuitions are not, this is definitely an easier problem. It's no harder than graph isomorphism. And, if you look at what's going on with satisfiability, unique SAT has essentially the same complexity as ordinary satisfiability. We don't know a theorem like that here. If you try to mimic that proof, it just doesn't work. So anyway, the graph automorphism reduces with this more restrictive notion of reducibility to MKTP. And I will talk about the proof of that too, but what is relevant for the discussion where I want to get to answer Catherine's question, is there's this theorem by Turan that says that the determinant AC0 many 1 reduces to rigid graph isomorphism. Why is this relevant? Because there's another theorem that we have that says rigid graph isomorphism AC0 many 1 reduces to MKTP. So you put this together and we get that the determinant AC0 reduces to MKTP. And the determinant is actually a pretty big subclass of P. So the determinant is roughly the same thing as sharp L, counting the number of paths accepting computations in an NL computation. And so this is a pretty respectable sized subclass of NP, or of P, that reduces in a many 1 way to MKTP. This reduction, by the way, is non-uniform. So what about uniform reductions? Well, actually, let me just mention since the determinant is hard for this big complexity class, we get a corollary MKTP is not an element of AC0 mod P for any prime P. This is a circuit class lower bound that we do not know for MCSP. None of this do we know for MCSP. And this is, it should be a pretty low bar to jump over to prove that minimum circuit size problem is not in this really tiny complexity class. That should be something that we ought to be able to do, but we still can't. Okay. So, uniform reductions. If you
That's non-uniform AC0.
non-uniform AC0. Pardon?
In a corollary.
Either one. I mean, in particular, the stronger result is it's not in non-uniform AC0 mod P. But for MCSP, we don't even know if it's in uniform AC0 mod 2. Okay. So this follows pretty easily from this proof, which is a probabilistic reduction. And most of the time where you see something that is done for non-uniform circuits, it arises from a probabilistic reduction. And probabilistic reductions can usually be de-randomized. And thus, the following is not too surprising. If D space n is not in size 2 to the epsilon n for some epsilon greater than 0, then the determinant, I'm just going to use this notion, capital G reducibility reduces to MKTP, where A G reduces to B means a log space uniform AC0 conjunctive truth table reduces to B. This is ugly. This is overly technical looking because we're using a particular, maybe not the most natural uniformity condition, and we're looking at conjunctive truth table reductions. Oh, actually, there's one more restriction that are natural in the sense of psi and cabinets. And I really want to have you ignore all of this seemingly needlessly technical stuff. And so what's G stand for? It stands for groovy. You know, this is a groovy reduction. You know, so in particular, it's uniform. Where am I going with this? The whole point of doing all this to answer Catherine's question, theorem. Let MKTP relative to A be in PA/Pauli. This is a strong condition, but it's not as crazy as you might think. I'll present a bunch of A's for which this holds. Then the following are equivalent. 1, parity groovy reduces to MKTPA. 2, there exists an epsilon greater than 0 such that D space relative to A, n, is not in size 2 to the epsilon n. And 3, the determinant groovy reduces to MKTPA. So, sure, this notion of groovy reductions, don't use this notion outside of this room, even though I know this is being videoed. Don't, you know, it sounds like a ridiculously technical notion, but it is equivalent, you know, reducibility under that notion gives us equivalence to a pretty natural, important question about circuit size. So maybe there's a way you could prove a better version of this result using a less technical notion. But at least this does go through. And what does it tell us? Let's look at the case where A is the empty set. If A is the empty set, what do we have? We have statistical zero knowledge, which is a pretty big complexity class, is in BPP relative to MCSPA, and the determinant G reduces to MCSPA. So in fact, let me write this way. SZK, everything in SZK, BPP Turing reduces to MCSPA. Now let's let A get more powerful. If A is equal to QBF, what do we have? P space is actually equal to BPP to the MCSPA, because MCSP relative to QBF is complete for P space. So as the notion of, as A gets more powerful, the stuff reducible to this problem expands from a pretty reasonable subclass to P space. Well, that's what you expect. If a problem gets more powerful, more stuff reduces to it. But parity doesn't G reduce to MCSPA. What? With an empty oracle, you get a pretty reasonable subclass of P. You increase the power to get, something you get a set here that's really P space complete, and you can't even reduce parity to it. Well, this is not really so crazy. It's because this is a uniform reduction we're talking about. And these G reductions are non-adaptive reductions, which means that on, let's say you've got a low Kolmogorov complexity input, the only queries you can ask are sort of low complexity queries. And so you can only ask kind of meaningless queries, basically, and so you can't get much use out of the oracle. So I think it's maybe quite plausible to think that MCSP and MKTP with no oracles are not going to be complete under uniform, let's say, many-one or maybe even uniform Turing reducibilities. But under probabilistic reductions or non-uniform reductions, who knows? I mean, you do get a reasonable subclass under non-uniform. Well, even here, this is even under uniform reductions. So I think this theorem is certainly not the final statement, but this is about as far as we've been able to come. So two very different types of things happen. For probabilistic and non-uniform reductions, when you've got a reasonably strong notion of randomness, like space-bounded randomness, something that's p-space complete, then the set of random strings is going to be complete under these powerful reductions. But under the uniform reductions, it doesn't look like that's provably it's not the case, at least for this particular weak class of uniform reductions. And with the empty oracle, certainly if you can reduce this much to this problem, we ought to be able to reduce more, but we don't know more. And actually, in this column, every occurrence of at least these two occurrences of MCSP should be MKTP. I wrote the wrong letters there. MKTP. Here, these non-reducibility things, they actually hold for both notions down here, MCSP and MKTP. Okay, so that's part of the story I wanted to tell you. That, we wanted to investigate MCSP and MKTP relative to oracles, in part to get a handle on what's happening without the oracles, as well as because it gives us different notions of complete sets for classes that we care about. And what we've learned is that at least for uniform reductions, something counterintuitive happens. You can this is actually a conditional result. This is conditional on the likely fact that linear space requires exponential sized circuits, assuming D space n is not in size 2 to the epsilon n, which has to be true. Okay, so questions about the big picture, and then I'm going to go back and actually prove some stuff, as much as I've got time for. In particular, if you're completely lost, this is a good time to have me go back and try to make sense of some stuff. Okay, so I'm going to go back and prove those two statements. And in fact, I'm just going to prove easier versions of those two statements. Instead of doing the ZPP Turing reducibility, I'm just going to do it for p-poly reductions. And instead of doing log space Turing, I'm just going to do it for log space many 1. This will give you the main ideas of what's going on. So let's do the first one. Remember yesterday, or 2 days ago, when we proved graph isomorphism reduces to MCSP, we used the Hostad-Impagliasso-Levin-Luby generator. And that's great when you are working with polynomial time computable functions that you want to invert. Here we're going to use a different pseudorandom generator, Babai, Fortnow, Nissan, Vigderson, that tells how to use a hard to compute function in order to build a pseudorandom generator in the following sense. You pick absolutely any function at all, then there is a generator that Babai, Fortnow, Nissan, Vigderson tell us how to compute. It takes n to the epsilon bits to n bits, such that if you have any test that distinguishes random from pseudorandom, so let's say the test accepts a large proportion of the random strings of length n and hardly any of the pseudorandom strings of length n, then you can use that test with polynomial-sized circuits to compute F. And the bad news is that F, yes, they tell us how to compute it, but they only give us a p-space algorithm to compute it. A p-space algorithm with oracles for F. On the other hand, the good news is that for many F that we care about, P to the F is equal to P space to the F. In particular, that's true if F is QBF. So that means that this generator is actually efficiently computable with oracles for F. Okay, so now this is basically a one-liner because with MCSP we can have as our test T the set of all x such that KT QBF of x is greater than or equal to, let's say, length x over 2. This is something that we can compute with MKTP as an oracle, and in this regime, that's as good as MCSP. So this is a terrific test to distinguish random from pseudorandom because the output of this generator has really small KT QBF complexity, and a random string, of course, has got huge, linear sized KT complexity. So, therefore, if I want to compute QBF, I can do it with MKTP QBF or MCSP QBF as an oracle because of this. QBF is in P poly relative to this test. So again, this is this hammer we've been using over and over again. With the pseudorandom generators, we can show that use de-randomization techniques to show that these tests are hard to compute. So that's kind of like what we've already done. Let's do, but we used a different generator. Now let's do this non-completeness result. And for many one reductions, it's particularly easy. So how do we do this? Let's let A be something that's in exponential space and not in P space. Then the set 1 to the x such that x is in A, which I will denote as the unary version of A, is in P space. And if this is not a known trick to you, trust me, this is a one-liner. This is a very easy fact. And if we are assuming that this set is complete under log space many-run reductions, then let's say let F compute a log space many-one reduction from the unary version of A to, let's do it for MKTP QBF. The same thing will basically work for MCSP QBF. And note that the KT QBF complexity of F of 1 to the n is logarithmic. In fact, you don't even need the QBF oracle for this. any unary string, if you do a polynomial time reduction on it, is going to have logarithmic complexity. So this is a trivial observation. So that means that given x, we can try all short descriptions D and see if they happen to describe f of 1 to the n. Now f of 1 to the n, or f of 1 to the x, let's say, this is a minor technical point. If we're given x as input, 1 to the x is, of course, exponentially bigger. On the other hand, f of 1 to the x is also only exponentially bigger. And we can compute each bit of this using a small amount of space because f is a log space computable function. So this, log of exponential is log. And therefore, in polynomial space, we can compute each bit of this and compare it with, with what our universal machine on a short description is getting. And so we can try all the short descriptions, and therefore we can determine kt of f, or kt QBF of f of 1 to the x, because we know exactly which short descriptions work for us, and we can find the shortest one and see how much space we used. And thus, using just polynomial space, we can figure out exactly the complexity here and solve in polynomial space membership in A, but we chose A to be outside of P space. If that went by too quick, the message is some pretty easy tools suffice to prove non-completeness. And the references, you can, I'll give you the pointers, or I'll give the organizers the pointers to the places in the literature. You can read up on that if you want. So, so we proved that. And in the next 5 minutes, or 2 minutes by that clock, I can try to sketch how some of this works. Do we have energy for that? The thing to note here, particularly, maybe let me just tell a story about this rather than launch into the proof. If A is powerful enough so that linear space relative to A actually requires exponential sized circuits. And we think that's pretty, you don't have to be very powerful for that to happen. Oh, this is size A. That was a bad omission. Yeah, as A gets powerful, it actually becomes more likely that this inclusion does hold, right? If A is equal to QBF, linear space relative to QBF, well, that's just P space. And of course, P space does have linear size QBF circuits. Okay, so as A gets more powerful, at some point this stops holding. And at that point, not only do you not get the determinant, but you also can't even figure out if the number of ones in your input is odd or even. So you either get a pretty reasonable class or you get basically nothing, which is surprising to me. That there's this particular cutoff point where that happens. And I promised you that I'd say something about this condition. Maybe that's what I should actually do now. You may or may not remember that p-space is alternating time polynomial. If you don't know what alternating machines are, go out and read about them. That's really a beautiful theory. It's like it's a generalization of nondeterminism, where you have existential, which are nondeterministic states, and also universal states. And the polynomial hierarchy is alternating time polynomial with a constant number of alternations. And thus, in between, if you have alternating time n to the order 1 with alternations bounded by some a of n, where a of n is non-constant, like log n or log star n or cube root of n. If you look at any a that's complete for this class under a reasonable notion of reducibility, then this is going to hold. Because you can solve this problem with just one level of alternation relative to a, and then you can reduce that to a itself. So pretty low down in p-space, this starts holding absolutely. So even though this looks like a strong condition, it holds a lot of places in p-space for problems we would care about. So in the time remaining to me, let me thank the organizers for bringing me here, as I didn't do that before. But I'm having a great time, and I hope you found this entertaining also. So that's the end.
How far are we from knowing what we know for MKTP for MCSP?
I can't imagine that there's a huge barrier to doing this. So what I had actually hoped to have time to do was actually prove some of the results that we have for MCSP versus for MKTP that don't hold. In particular, this reduction from rigid graph isomorphism. It's actually a pretty simple reduction. If you've got two graphs, G0 and G1, you pick a random string W such that the length of W is t, so you've just got t bits, and pick random permutations, pi 1, pi 2, ... pi t. So you've got t random permutations. And now if you look at pi 1 of one of these graphs, where which one you pick is given by the first bit of W, and then you apply pi 2 to the second of those, you pick the next graph and apply random permutation pi 2 to it, all the way up to pi t GWT. In the case, and let's call this string Z. So if G0 is isomorphic to G1, that implies that the time-bounded Kolmogorov complexity of Z is about n squared, because we need to know what the graph is. It's an n by n graph, plus t times n log n. You give the t permutations. Whereas if G0 is not isomorphic to G1, that implies that the time-bounded complexity is greater than or equal to, if these are not isomorphic and they're rigid, then given Z, let's say we don't worry about the time-bounded. The complexity, which is the time-bounded, kt of Z is greater than or equal to k of Z, which is greater than or equal to, well, we can get all of the bits of W back because we can figure out which the first graph was that was permuted, which was the second. We can get all those bits back, and we can get all of the permutations back, t times n log n. We get all the permutations back. And so if t is enough bigger than n squared, this will be bigger than this, noticeably bigger. And so, so what do we get from that? That's the reduction. If we pick a random string W, then with high probability, pick these things at random, then with high probability, so this is actually with high probability. With high probability, we will have something that's got high complexity. And so this is a witness that, a proof of non-isomorphism. Because, we'll ask the oracle, does this have high complexity? It says yes. We'll say, aha, they were not isomorphic. And otherwise, it's lower. But there's not really such a big gap here. We're basically saving 1 bit each time we repeat this. And for KT complexity, that's okay. But for circuit size complexity, these are just too close to each other to get this argument to go through. So all we really need is to have a different approach that's more suitable for circuit size complexity. It doesn't seem like it ought to be too much to ask for, but we haven't found it yet. And other people are looking at it too. So it's not, we're all too stupid. It's not just me.
So somehow I understood this hardness proof. So for this line of research, where it shows the easiness of this CSP?
So the easiness is the sense that it's not hard, right?
So you want to show some evidence it's not an NP-hard.
Right. So, so actually, Ryan Williams has a lovely theorem that I didn't state, that I should have stated. I mean, in some sense, it's implicitly here, but Murray and Williams showed that parity does not M-reduce via deterministic time cube root of n to MCSP or MKTP. So what is a sublinear time reduction? It's a reduction that computes, here's our input W, and here's f of W. And if I want to compute the ith bit here, f of W, the ith bit, is computable from Wi in time less than or equal to, let's say, deterministic time, length W to the 1/3. So you can get each bit quickly. Now, this might seem like a pretty restrictive notion of reducibility, but all of your favorite NP-complete problems, everything in Gary and Johnson, I think, is complete under log time reducibility in this sense. You can actually have the output be very highly structured so that you can compute each bit quickly with random access to the input. So this is actually a pretty nice result. You're going far beyond log n to something polynomially related to n.
But is that somehow also related to this log space uniformity of the circuit because of that? So we have a circuit size that when you define how you reconstruct circuit and you get the log space.
So this is saying that parity does not reduce to MCSP via a particular type of uniform reductions computed by circuits where each bit of the output depends on only a very small number of bits of the input. So you can phrase this as a notion of uniform, so if the number of bits here is constant, that would be an NC0 reduction. If you allow it to be much bigger, then it's an NC, we don't really have a notion, a nice name for that. It turns out that for reasonable complexity classes, complexity class AC0 M reduces, hardness is actually equivalent to NC0 hardness. So when we show that MKTP is hard for the determinant under AC0 reductions, for free we actually get that it's complete under NC0 reductions, but we only have this non-uniformly, so we only get this non-uniformly. So what's really going on here is that Murray-Williams' non-hardness result is about uniformity in a big way. And when Shuichi Hirahara and I started working on this project that ended up proving this, we thought uniformity can't be what's really happening here. We thought surely we ought to be able to prove that parity does not NC0 M reduce to MKTP, but in fact it does. So that was the first surprise. There have actually been a lot of surprises.
But even that one, so that basically somehow states this kind of reduction for AC0 reduction, my interpretation is you can always somehow localize it, something like that, right? Yeah, that's not going to have a global impact. Something like that. I see. Thanks. Any other questions?
This is something that we have tried a bit, not very seriously. Are there studies of MCSP on specific classes, like for example symmetric Boolean functions?
So people have definitely looked at MCSP restricted to different classes of circuits. So for instance, AC0 circuits of a particular depth, or TC0 circuits of a particular depth. And so, pardon?
Do we know they are easy unconditionally?
So here a very strange thing happens. So MCSP for TC0 circuits of particular depth, I don't know, let's say 5, is easy implies Blum integer factorization is in P. MCSP for TC0, or for AC0 depth, I don't know, K is easy, implies Blum integer factorization is in, something like deterministic time 2 to the n to the epsilon sub k. So you get fast algorithms there. And MCSP for DNF formulae is NP complete. So you might think, okay, we get weaker conclusions because we're talking about weaker circuits. And well, that continues here. And then you get down to depth 2, and it's actually NP complete. So our intuition can mislead us many different ways. We still don't know what's going on.